In the work I'm going to present, we study the blocked waiter wake-up problem and explore the method to mitigate the problem for multi-threaded applications in virtual machines. So this is a joint work between NGIT and Intel Lab Pittsburgh. As we know, we enter a multi-core era, right? So we see the number of cores in a computer keep increasing. At the same time, the same trend also happens in virtual machines. So we see the number of virtual computing units or virtual CPUs or vCPUs keep increasing in virtual machine. Now in Amazon EC2, Amazon offers instances with 32 virtual CPUs. So with more and more virtual CPUs in the same virtual machine, a natural question to ask is whether applications can improve their performance by taking advantage of more virtual CPUs in the virtual machine. We want to ask this question because virtual CPUs actually behave differently with physical CPUs. They are actually schedulable execution entities. For example, in KVM, virtual CPUs are actually a normal thread scheduled by Linux scheduler. So in this table, we summarize the behavioral differences between virtual CPU and physical CPUs. So if CPUs are busy, busy virtual CPUs can make continuous progress in parallel, but virtual CPUs may be preempted, suspended without notification. If CPUs idle, when some computation becomes ready, physical CPUs can be available immediately, but virtual CPUs must be rescheduled to continue computation. So we know that applications and guest operating systems are designed for physical CPUs. So they expect the behavior of a physical CPU, which cannot be fully implemented on virtual CPU. So what's the performance indication? The difference between virtual CPUs and physical CPUs can greatly impact synchronization performance. We all know that there are two types of synchronizations, right? Busy waiting. That means that a thread spins when it waits at a synchronization point. The other type of synchronization is called blocking. So a thread is blocked when it's waiting at a synchronization point. With the busy waiting synchronization, because virtual CPU may be suspended at any time, the lock holder preemption problem will be caused. So the lock holder preemption problem is caused when the virtual CPU holding the spin lock is preempted. So other virtual CPUs waiting for the lock must spin for a long time to get the lock. So the lock holder preemption problem reduces scalability because it significantly increases the length of the critical section. It reduces efficiency because of the spinning. This problem has been well studied, and there is a hardware solution implemented in CPU. So in this work, we're focusing on the other type of the synchronization, blocking, and we study the blocked waiter wake-up problem, or BWW. So this problem was mentioned in a technical report, but never received enough attention. So this problem was caused by idle virtual CPUs resumed execution very slowly. So let's look at what's the BWW problem. BWW is that waking up blocked threads takes a very long time on idle CPUs. It takes a long time because virtual CPUs have to be rescheduled before they run any thread. They must be rescheduled because they were preempted or suspended when they become idle due to the lack of runnable threads. But how long does it take to wake up a thread? It depends. Depends on the availability of the hardware resources and the cost of virtual CPU switches. Why we need to study the BWW problem? Because it can significantly degrade the performance of synchronization-intensive applications. First, it may increase the execution time of the applications in VM because computation is delayed. Secondly, it may cause unpredictable performance because you cannot predict how much the delay is. Thirdly, it may significantly reduce the system overhead because of the actual overhead introduced by the vCPU switches. To illustrate this point, we run Spark benchmarks in VM with dedicated hardware. And in this figure, I show the performance slowdown of these benchmarks. As we can see that for some synchronization benchmark, their performance can be significantly slowed down. The slowdown is so much, it's surprising, so we, to better understand this problem, we study the Wakeup operation in two CPUs. So we run two threads on two CPUs. On one CPU, a thread calls pthread mutex log. It enters the critical section. At that time, the thread on the other CPU calls pthread mutex log and try to get the log. It fails, and it's blocked because the log has already been obtained by the thread on CPU A. After that, CPU A calls pthread mutex log to release the log. Because there is a waiter for the log, so the thread on A must notify and wake up the waiter. So we measure time to wake up the thread and inspect what the operations are to wake up the thread. If the CPUs, I mean CPU A and B, if they are physical CPU, to wake up the thread, basically A sends an interrupt to B, and B carry out rescheduling and wake up the thread. If we wake up the thread on virtual machines, I mean the two CPUs are virtual CPUs. To wake up the thread, the interrupt must be handled by virtual machine manager. The virtual machine manager must also activate the idle CPU because the idle CPU was preempted. To reschedule the idle CPU, we need hardware resources. So here we must wait for hardware resources become available. If it's necessary, we must also preempt a running virtual CPU to make available the resources. When the resources are available, we reschedule the idle virtual CPU. After that, on the virtual CPU, we reschedule the thread in the guest OS. And now the thread is woken up. So you can see that it may take very short time on hardware, and the time latency is rather fixed. But it takes much longer time on virtual CPU, and the latency is variable. Because you never know how much time you have to wait for the hardware resources. So these operations are to switch virtual CPUs. They are the major sources of overhead and the variation. Based on our experiment, they contribute more than 80% of the latency. So the key to mitigate this problem is to reduce harmful virtual CPU switches. Basically, there are two general methods to reduce the virtual CPU switches. One method is to retain the resources at a higher level of software stack. This is to prevent idle virtual CPU from being suspended. For example, we can use some idling operation in guest operating system to prevent idle virtual CPU yielding hardware resources, so we can let it spinning. But resource retention method may cause resource underutilization. Consider the case in which virtual CPU may spend a lot of time idle. So if we let this virtual CPU spin, the system throughput may be significantly reduced. So we must balance the cost of spinning and virtual CPU switch and use the operation that costs a smaller cost. The common method is to use a timeout for spinning. But the problem is still there. For a long idle period, when timeout happens, we must pay both overhead of spinning and the virtual CPU switches. The other method to reduce virtual CPU switches is called consolidation scheduling. So basically, we consolidate busy period and coalesce idle period on virtual CPUs. With conventional scheduling in guest OS, threads are evenly distributed. For example, we run 2 threads on 2 different virtual CPUs. So this is to maximize throughput. But with consolidation scheduling, we deliberately keep some virtual CPU idle and consolidate this thread to other virtual CPU and keep this virtual CPU busy. So the effect is that with conventional scheduling, there are a lot of virtual CPU switches. With consolidation scheduling, the idle core is suspended automatically by virtual machine manager to save resources. And we keep the basic core active to avoid virtual CPU switches. So the result is that the virtual CPU switches can be reduced. But there's still some problem. The problem is that the active virtual CPUs may be overloaded. That leads to low performance. So in our solution, we combined both approaches. With consolidation scheduling, we reduce the long idle period, which cannot be effectively reduced by resource retention. With the resource retention method, we manage short idle period, which cannot be effectively eliminated by consolidation scheduling. So for this example, we have 3 threads, we have 3 virtual CPU. Instead of running 3 threads on 3 virtual CPU, we consolidate these 3 threads on 2 virtual CPUs. We don't consolidate these 3 threads on a single virtual CPU to avoid overloading that virtual CPU. So as you can see, there's still some idle period, but long idle period are reduced. Then this short idle period can be eliminated by idling operations in the resource retention method. So this is the basic idea. A challenging issue that Gleaner must handle is to prevent overloading. There are 2 causes of overloading. One cause is that the workload is too heavy for active CPUs. For example, we consolidated 3 threads onto this one virtual CPU. That may overload that one active virtual CPU. The other cause is that the workload cannot be evenly distributed among active CPUs. So some active CPUs may be overloaded, and some other active CPU might be underloaded. So that's usually caused by long execution period in the threads. To prevent overloading, Gleaner gradually consolidates workload threads. It only proceeds if it expects that the virtual CPU utilization would not be too high after the consolidation. At the same time, it's guaranteed that the workload can be evenly distributed among active virtual CPUs. Gleaner also monitors the throughput of the workload. It stops consolidation when it observes that the throughput starts to reduce. If you want more details, please read the paper. So to test the Gleaner, we implement a prototype and run our experiment on a 16-core Dell server. The virtual machine manager is KVM. And on KVM, we built virtual machines with 16 virtual CPUs. And we select benchmarks from PASEC 3.0. And we also select some other benchmarks like MySQL driven by SysBench and Micro Benchmark. In the first experiment, we want to study how the application performance change when Gleaner is enabled on a virtual machine with dedicated hardware. So we run one virtual machine That virtual machine has 16 cores, 16 virtual machines, 16 virtual CPUs. So basically, there are 16 virtual CPUs on 16 physical CPUs. So in this figure, I compare the slowdowns of the parsec application for the system with Gleaner and the system without Gleaner. So the slowdowns are relative to the bare metal performance of these benchmarks. As you can see, Gleaner can significantly reduce the slowdown of these benchmarks. The second experiment is to demonstrate that Gleaner can improve application performance on oversubscribed system. So we run 2 virtual machines. So there are 32 virtual CPUs on 16 physical cores. So in one virtual machine, we run Spark benchmark, and in the other virtual machine, we run matrix multiplication. In this figure, we show the relative performance of the benchmark on the system when Gleaner is enabled. So the performance is relative to the stock system without Gleaner. The 100% relative performance means that the benchmark has a similar performance on both systems. As we can see, for quite a few benchmarks, Gleaner can significantly reduce their execution time. Gleaner reduces the execution times by a larger percentage on oversubscribed systems compared to the system with dedicated hardware. That's because these applications were degraded by larger percentages on the oversubscribed system. The Gleaner can improve application performance by up to six times on the oversubscribed system. The last experiment will show that Gleaner can improve the overall system throughput. Because Gleaner can reduce the overhead introduced by virtual CPU switch, it can improve the system throughput. To demonstrate this point, we run multiple identical virtual machines. So we increase the number of virtual machines from 1 to 5, and we measure the throughput. This page shows the relative throughput of the system with Gleaner enabled. As we can see that for dedupe, Gleaner can improve system throughput by 3x. For MySQL database, we can improve system throughput by almost 2x. To conclude my talk, due to the differences between virtual CPUs and hardware CPUs, synchronization becomes more challenging on virtual machines. So focusing on the blocking synchronization, we study the BWW problem, which is caused by waking up blocked threads being delayed by switching back idle CPUs. It can significantly reduce the application performance and the overall system throughput in virtual machines. To mitigate this problem, the key is to reduce harmful virtual CPU switches. So in our solution, we combine 2 methods, resource retention and consolidation scheduling. Our tests show that our solution can improve application performance significantly by up to 16x and system throughput by up to 3x. Thank you. I'm happy to take questions.
I'm Junji from Toronto. Could you go back to the slide that you showed the comparison results?
Which
comparison?
This page or?
Previous one.
This page, right?
Yeah, this one.
Okay.
It looks like we saw 2 outliers here. So like the last one, X264.
Yeah.
Actually, with your Gleaner, you actually increased the slowdown. And also we saw Caneel.
Yeah.
Also, could you explain a little bit?
You know that one important issue Gleaner must address is to prevent prevent overloading, right? Because
Yeah.
overloading degrades performance.
Okay.
Because our implementation is at the user level, it cannot completely remove the performance degradation caused by overloading. So that caused the performance degradation in these two benchmarks.
So it's because of overloading.
Right.
Okay, thanks.
Really quick question. Did you run this on any other hypervisors?
Pardon?
Did you test your results on any other hypervisors? So like your 100 microsecond Wakeup, is that specific to KVM? Did you use VMware?
We tried on for hardware CPUs, we tried on Linux without hypervisor. So for the data on virtual machine, we use KVM. I don't know.
You didn't try Zen or VMware?
No.
Okay, thank you.
Okay, thank you.